Welcome to Review Lane.
Great to be here.
Today we're doing a deep dive into machine learning. You probably hear it called ML a lot.
Yeah, it's definitely everywhere.
Yeah.
Think about things like medical diagnosis help, or even just your social media feed suggesting connections.
Right. And looking through the sources, it feels, well, maybe more accessible than people assume.
I think so.
Yeah.
So our goal today is really to unpack that. We want to pull out the core ideas from the materials we looked at, just so you can get a solid grasp on what ML actually is and how it gets used,
Yeah.
especially if, this is all pretty new to you.
Okay.
At its heart, really, it's about building computer systems that can learn from data. They make predictions or they find patterns without a person having to sit down and spell out every single instruction.
Okay, learning from data. Let's break that down. How does that even work? Like, how do you give data to a machine? The sources talk about picturing it like a table.
Exactly, like a spreadsheet almost.
Yeah.
Each row is an item you care about. It could be a customer, it could be a product, maybe even a flower, like in one of the classic examples.
And the columns.
Those are the details about that item, the properties or what we call features. So for a customer, it might be age, location, for that flower, maybe petal length, petal width, things like that.
Gotcha. So that table idea is key. And you mentioned learning. One big way is supervised learning.
That's right, supervised learning. That's when your data table already includes the right answer for each row. We call that the label.
So the machine gets shown examples, but it also gets told what the correct outcome was for those examples.
Precisely. It sees, say, lots of flower measurements and the correct species name for each one.
Yeah.
Or maybe transaction details and whether that transaction turned out to be fraudulent or not.
Okay, learning from known outcomes. Makes sense. And there are different types of this supervised learning.
Yep, two main flavors. First one is classification. The idea here is to predict which category something belongs to.
Like sorting things into buckets.
Exactly. Is this email spam or not spam? Is this picture a cat or a dog? The sources mentioned the IRIS dataset. That's a classic. You use flower measurements you already have, where you know the species, to predict the species of a new flower. You're classifying it.
Okay, predicting a label, a category name, that's classification. What's the other type?
The other main one is regression.
Regression.
Here, you're not predicting a category. You're predicting a continuous number, a value.
Ah, okay. So like predicting how much a house will sell for based on its size, location, stuff like that.
Perfect example. Or maybe predicting a person's income based on their education and job title. It's predicting a specific point on a numeric scale, not just picking from a predefined list.
So you train it on like lots of house data where you know the features and the final sale price, and then you ask it to estimate the price for a brand new house listing.
Yes, exactly. And that brings up, honestly, probably the most important challenge in supervised learning: generalization.
Generalization.
Yeah.
Meaning it has to work on new stuff.
Right. You don't just want a model that perfectly memorized the answers for the data you showed it during training. That's easy. The real test is, can it make accurate predictions on new data? Data it's never encountered before out in the real world.
I remember the sources had a good, simple example for this. Like, someone tries to predict who buys a boat,
Oh yeah, your boat example.
and they come up with some really weird, specific rule based on just a few people, like they have to be exactly 58 years old or are not divorced. Works for the training data, maybe, but it's useless otherwise.
That's a perfect picture of overfitting. The model learned the training data too well, including all its quirks and noise, instead of the actual underlying pattern. It fits too closely.
And the opposite is underfitting. Too simple.
Yeah, underfitting is when the model is just too basic. It doesn't capture enough of the pattern, even in the training data. So finding that balance, that sweet spot where it learns the real pattern well enough to generalize, that's the key.
Okay, so let's say you have your data, if it's classification or regression. There are different actual techniques, right? Algorithms. The sources mention things like decision trees or k-nearest neighbors.
Yeah, lots of different tools in the toolbox. K-nearest neighbors looks at similar examples it's seen before. Decision trees build sort of branching rules. And then you have things like random forests, which actually combine lots of simple models, like many decision trees, to become really powerful.
How do you know which tool to use? Or even how well any of them are doing?
Ah, good question. That's where evaluation comes in. And the sources really stress this. Just looking at accuracy, like the percentage it got right, often isn't enough.
Why not? Isn't getting it right the goal?
Well, yes, but imagine you're trying to detect a really rare disease. Maybe only 1% of people have it. A lazy model could just predict no disease for everyone.
Okay.
That model would be 99% accurate, but it's completely useless because it never finds the actual cases you care about.
Ah, I see. So simple accuracy can hide problems. That's where that confusion matrix thing comes in. And precision and recall.
Exactly. The confusion matrix basically breaks down the predictions. It shows you how many times did we correctly say yes, how many times did we correctly say no, but also how many times did we say yes when it was actually no, that's a false positive, and how many times did we say no when it was really yes, a false negative.
Like the cancer screening example they used.
Right. Precision asks, out of all the times we predicted cancer, how often were we right? High precision means few false alarms. Recall asks, out of all the actual cancer cases, how many did we catch? High recall means we didn't miss many cases.
And which one matters more depends on the situation. Missing a cancer case, a low recall, is probably much worse than a false alarm, which is low precision.
Precisely. The cost of different errors determines which metric you focus on.
Okay, that's really helpful. Now, what if you don't have those labels? No right answers in your data table.
Right. That takes us into the world of unsupervised learning. Here, you've just got the data itself, the features, but no predefined answers. The goal is to find some kind of interesting structure or pattern within the data.
Like grouping similar things together automatically.
Yeah, that's a big one called clustering. You might want to find natural groups of customers based on their buying habits, for example, without knowing beforehand what those groups might be. Or group news articles by topic.
What else can you do without labels?
Another common use is dimensionality reduction or transformation. Sometimes you have tons and tons of features, like hundreds of columns. Unsupervised techniques can help boil that down to just a few key dimensions, maybe just 2 or 3, so you can actually visualize the data on a chart and see if there are clusters or patterns.
But how do you know if the patterns it finds are good if there's no right answer to check against?
That's the tricky part with unsupervised learning. Evaluation is often more subjective. You might need a human expert to look at the clusters or the transformed data and decide if the patterns discovered are actually meaningful or useful for the task at hand.
Right, that makes sense. And building a whole system, like for predicting house prices or finding customer segments, it's not just one step, is it? You have to prepare the data, train the model, evaluate.
Absolutely. It's usually a whole sequence of steps. Cleaning the data, maybe scaling the features, choosing and training the algorithm, evaluating it properly. The sources mentioned using tools like pipelines, especially in libraries like scikit-learn.
Why are those important?
Well, they help you chain all those steps together logically. And crucially, they help make sure you evaluate your model correctly, especially avoiding accidentally letting information from your test data leak into your training process, which can give you overly optimistic results. Pipelines help keep that process clean.
Okay, so wrapping this up, understanding these basics, the data table idea, supervised versus unsupervised, classification versus regression, and really thinking about evaluation beyond just basic accuracy. It helps you make sense of the ML systems you hear about or even interact with.
Definitely. It demystifies it a bit. It shows that it's not magic, It's about making smart choices, picking the right technique for your problem, getting the data ready carefully, and being rigorous about checking if it actually works in the way you need it to. It often takes some experimentation.
Absolutely. So thinking about how ML can uncover these patterns, maybe things humans wouldn't easily spot, it makes you wonder, doesn't it? What kinds of insights or maybe even challenges could be hiding in data that relates to what you, the listener, are interested in or work on? What could ML potentially reveal there?